next speaker is actually the third student talk of the afternoon. I neglected to mention earlier that Fabian Antonios' talk was a student talk. The next talk is by Jonathan Menu, who will talk about TW Hydra, multi-wavelength interferometry of a transitional disk.
Okay, I hope this works. So hi, my name is Jonathan. I'm from the University of Leuven in a small country called Belgium. So I will talk about TW Hydra. This object might at least ring a bell to you because, well, as you have heard, most of the talks before my talk have already mentioned the object. And the reason for that, it's a very, it tends to be a very popular object. It's a transition disk object with a protoplanetary disk with a large inner hole. And I present to you multi-wavelength interferometry of that target. So this is work that I've been doing at the Max Planck Institute in Heidelberg, and where I work mainly together with Roy van Boekel and Thomas Henning. So as I said, TW Hydra is a protoplanetary disk with a large inner hole, a transition disk, and the reason why people tend to study these objects is because they really show that, or at least some of them really show that they are protoplanetary. So this is, these final years has been the first time that we really confirm that the name protoplanetary was not badly chosen, because we start seeing in some of these targets that they tend to have blobs inside them. These are two very recent results. And so it turns out that if you want to learn something about protoplanetary disks, then transition disks might be good candidates to do that. So TW Hydra has not directly confirmed a protoplanet inside a disk, but still it's believed to be a Rosetta Stone for understanding of the evolution of protoplanetary disk, as Nuria Calvet and her team mentioned in 2002. So the reason for that, it's the closest accreting T-Tauri star, so it's very close. It's it tends to be rather easy observable. Its disk is oriented pole-on, as you can see here in this Hubble image. And as I said, it has got an inner gap. Now, it has an inner gap, and people are convinced about that, so you can see it in the SED. But what the exact structure is of that inner gap is to a large extent unclear, or under discussion, I would say. So there have been people proposing large inner holes and small inner holes, then hybrid structures which involve both the large hole and small hole structures. And then there's recently even a self-luminous source proposed inside that disk to actually model the observations that they do in the mid-infrared. So a lot of discussion going on, and that's the motivation for this work. So there has been a decade of high spatial resolution observations, but then it's still not clear how the disk is actually shaped in the inner region. So that's a problem by itself, because it's the closest disk, so we might at least know how this disk is actually structured. Then, of course, if there's an inner hole, then there's some physics to learn about maybe, at least a disk dispersal and maybe planet formation itself. And then, of course, there's the modeling of the gas. So many discoveries have been reported for that disk. So there has been a cold water vapor observed, or very recently hydrogen deuteride, so a good tracer for H2 gas has been reported. And there was the talk of Charlie, 2 talks before, about the CO gas inside the disk. So if you want to model the gas in the disk, then the dust structure is like a boundary condition for that modeling. So it's the dust that determines the temperature structure inside the disk, and that's the reason why dust is important. So we have collected a big data set of data at high angle resolutions. So we have near-infrared interferometry using Pioneer, then sparse aperture masking data, mid-infrared interferometry using MIDI, sub-millimeter interferometry using SMA, and then millimeter interferometry, a new data set observed with the extended VLA, so EVLA at 9 millimeter. Now, of course, if you want to model the data, it could be that, by coincidence, one of the models that I have shown you before has already all properties to model exactly all that data. So what we have done is started with taking the most interesting models and to see whether they reproduce the data. So I don't have the time here to go into detail, but basically 4 conclusions can be made. The first one is that models with small grains, so with only micron and submicron grains, which are proposed, for instance, for the disk, do not reproduce all data that we have, so there's definitely the need for large grains inside the disk. And it's important to do a full radiative transfer modeling, because there tend to be, there are models which don't take into account complete radiative transfer, and where we see evidence for shadowing effects which are not taken into account. SED modeling is degenerate, again a reconfirmation, so the models tend to reproduce the SED pretty well, but then SED modeling, these models have different properties or different distributions of the dust, and so the modeling is degenerate. And special care is to be taken in the millimeter, because there is old VLA data available, but the new data tends to have a much higher signal to noise, so there's new information available, information that was not taken into account, of course, by these old models. So for the modeling itself, we have made use of a radiative transfer code, which we combined with a genetic fitting algorithm. I don't know if you're familiar with the principle of genetic fitting algorithms, but the idea is you start with a random set of models with random parameters, and you basically calculate the models, you calculate the chi-square corresponding to that, and you select the best models, and from the best models you calculate the next generation of models which are close to the parent models, and then you continue until you have a best model. So that's one way of determining the best fit model. So for the modeling itself, we have done, I guess there is some slide that has, okay, never mind. So we have done 3 models. There should have been one here in the middle. So there's, we started with a very simple model, then we have done some refinement here in the center. So the second model should have been that model, and with that refinement in the center, okay. And then the third model, for the second refinement, we had to actually concentrate the largest grains toward the center of the disk to reproduce our data. Now, I'm only going to talk about this first and the last model, so the fact that the model isn't there is not really, bad. Okay. So first, the simple disk model. So let's start very simple. We have an inner radius, an outer radius, a total dust mass in the disk. Then there's a surface density power P, so the way the dust is concentrated towards the center of or the edge, a maximum grain size, and an alpha turbulence parameter. So the turbulence in the radiative transfer code I use determines the settling of the large dust grains. So the lower the alpha, the lower the turbulence strength, the stronger the largest dust grains will settle inside the disk. So we have a model with 6 free parameters. And when we model the data, this is what gets out of it. So we have the SED, the sub-millimeter visibilities, then the millimeter visibilities, and the MIDI data. So the MIDI data I show you, this is a total spectrum observed by MIDI. And then at the 25-meter baseline and the 50-meter baseline, you basically get a measure for the spectrum of the inner part of the disk. So at 25 meter, we get a spectrum of the inner part of the disk, and at 50 meters we even get a more concentrated spectrum towards the inner end of the disk. So as you can see, SED reproduces more or less okay, and SMA data some problems over here, but also rather fine. But then the MIDI data, we see that we get the flux level quite okay. EVLA data seems to be completely off. So we move then directly to the last model. So based on the problems we have on the data, so really based on the data itself, we propose 2 refinements. So one is a rounded inner rim. So we have a radius at which the surface density drops off exponentially, which is this Rx. And then the W parameter determines the width of this region where the drop off happens. And then there's P large. P large is the surface density of the largest grains. So it turns out that we have to concentrate the grains larger than a radius of 100 micron in this case toward the center of the disk. So if you do that, so I show you here in the red dashed line the old simple disk model, and then the final disk model here in the blue full line.
So we see that we, well, reproduce SCD almost equally well, some problems over here. SMA data the data is reproduced a bit worse, but then if you look at the MIDI, the inner rim shape actually, well, we get to reproduce the data really well. And then the EVLA data, as you can see here, the single disk model with the same surface density for the small grains and the large grains was much more problematic than the disk model we have now. And these are then the parameters with some error estimates that we get out of that. So what we have done is we have done 2 refinements. So we have refined the rim shape. So we started with a sharp inner rim, then with a rounded. We went to a rounded inner rim. So what we basically have done is introduce an exponential dampening of the surface density of the grains at the edge of the disk. So this is not this is a simple parameterization of models that have been, that has been confirmed for the Herbig star HG100546. So what these people have done is they have done observations and hydrodynamical simulations to show that the rim is actually in agreement with this shape. So this is not simply, this is a parameterization of these hydrodynamical simulations, and they, had to assume that rim shape actually they have to assume that there is a 60 Jupiter mass brown dwarf inside the gap of this disk. So this disk also has a gap like TW Hydra, and this shape actually reproduced their data. So what we show is that for TW Hydra, at least the shape is in agreement, or we find that our MIDI data is in agreement with this profile. And that could be then a confirmation, but that should be, then confirmed by doing the hydrodynamical simulations, like in this case, that there could be a companion or a companion inside the inner 0.5 AU as a rough estimate. And then second, the decoupling between different grain sizes. So we had to decouple the largest grains from the smaller grains. So there have been many models proposed in the literature, theoretical models for the process of dust growth, and the process of dust growth has already been mentioned by Sean and also in the talk by Minke, that there are different regimes that determine the maximum size of the grains. So so what these people have done is they take a few very simple simulations. They do complicated simulations, but they show that you can reproduce them in a simple way. So we have, after a few megawatt years, typical simulations tend to have the largest grains in the inner region. Then there's a fragmentation limited regime, so the dust surface density looks like R to the minus 1.5 inside the inner side of the disk. And then the outer side of the disk is drift dominated. So the drift dominated, the larger grains spiral in toward the inner regions, and then the fragmentation limited is you determine the maximum grain size actually by the process of growth and then collisions, and you get towards an equilibrium of the largest grain size. So what we basically show with this study that if it is a coincidence or not, but it's indeed confirmed that that we find a centrally concentrated large grain size population. So basically all grains larger than 100 micron need to be concentrated towards the inner region. Then for the large grains, the surface density is in agreement actually with this profile. So this is then a confirmation of the second scenario, or the second the second result of these dust growth simulations. And then the small grains tend to be, have a surface density distribution of about 0.7. So they are not centrally concentrated, so they are also, more towards the edge of the disk, and then this could be a confirmation for this drift-dominated part in the disk. And then, I think I should end just with a very simple drawing that I made also for the other models. So this would be then our current estimate, or estimate for the current best model for the TW Hydra disk, or at least the inner region. So in summary, I have done radiative transfer modeling of data at the highest possible resolution that we currently get
model the inner, mostly the inner regions of the disk, because there's the large discussion going on. I've used automatic fitting, and every refinement that we have done was really based on the data. So we have started with the simplest disk model, and then we had to refine it based on the data. The models confirm earlier scales that are found when modeling individual data sets, but now we integrate data at all possible wavelengths. The RIM is in agreement with profiles from hydrodynamical simulations, so this is not a confirmation, but at least we show that there is an agreement, and if we want, basically, the next step could be to do this hydrodynamical simulation and to see if there's really a substellar companion and also needed inside the inner part of the disk. And then we have shown that there's a separate, or at least that we could model the data with a separated large grain population, so that we see evidence for the limiting dust growth regimes in the inner part or the outer part of the disk. And with these 4 conclusions or take-home messages, I would like to end. So thank you very much.
Okay, questions? Okay, 2 questions.
Do these, separation in grain sizes within the disk lead to a metallicity gradient within the disk?
So what we see is that it's basically the thing that Sean also explained, that if you look at these disks in different wavelengths, going from sub-millimeter wavelengths to millimeter wavelengths, that you see that the disk gets smaller. And one way to explain this, or the way that we have parameterized this, is taking the larger grains towards the inner edge of the disk. If this would have any further implications on the metallicity, I wouldn't know actually. So there's just the grain size, and there's not really we haven't done any variation in the composition inside the disk. So it is it could be tested, for instance, if different silicates need to be taken in the inner part of the disk. But I don't think that the metallicity is really an important parameter here. Or yeah, that would be my
answer. Do you constrain all the input parameters by this clever fitting, or are there a couple that you fix beforehand, specifically the turbulence?
No, so all of these parameters are more or less constrained by the fitting algorithm that we use. So basically, on the basis of all models that you calculate, you can get an estimate of the chi-squared surface or multidimensional surface, and you can really constrain the probability distribution associated to each of the parameters. And then you see basically that if you look at each of these parameters, that you have a distribution of possible values, but that other values don't seem possible. So you really constrain all the parameters, and that's also maybe one thing that you would expect if you take information into account of all wavelengths. So we have not introduced parameters of which we know that we wouldn't constrain them. Yeah, that could also be then part of the answer to your question. So we have only taken the parameters that we know that if you vary them, that you can see it in your data. So other parameters, for instance, one example could be the dust composition, which we have left fixed because you cannot constrain, or it's very difficult to constrain the dust composition itself on the basis of the data. So that could be then an example of a parameter which we have not valued and which we have left fixed. Yeah.
Right. And you say that the turbulence determines, for one, how fast the dust settles.
Yeah.
But another thing that would determine is how the spectral line shapes would look.
Yeah, that's but we model only the continuum emission. So
right.
Yeah.
Yeah. Thanks.
Yeah.
Okay, we actually just have time for one more question from Alicia.
So I also have a related question, which is, what do you assume about the stellar mass and temperature, neither of which are extremely well constrained for TW Hydra? And if you let those vary, how does that affect the other parameters in the model?
Yeah, okay, so we have left these values fixed to values that are generally taken in, and I know that there is quite a recent publication of a modeling of the near-infrared spectrum of TW Hydra, which gets to a very different effective temperature than the one that you see in the optical. So that would change the, well, I don't think it would change a lot on the geometry actually of the disk, because the geometry is most, for instance, if you look at the millimeter or the sub-millimeter, then it's only the temperature structure that will change a little bit, but the geometry, like the inner read.
Well, the amount of flaring changes if you change the central mass of the star.
That's sure. So we haven't varied that. Yeah, that's a good remark.
Okay, let's thank Jonathan again.